Hi, everyone. Thank you so much for viewing my talk today. My name is Rachel, and I'm a grad student at UC Berkeley, advised by Anna Rafferty from Carleton College and Tom Griffiths from Princeton. And our paper, A Rational Model of Sequential Self-Assessment, is really about metacognition, which broadly encompasses the study of how people reason about their own reasoning ability. It's a hot topic in both education and psychology because these groups are understandably really interested in how accurate students or adults are at inferring their own ability. And for a variety of reasons, there are different ways of measuring metacognition that have cropped up, including self-assessment, which is really common in the psychological literature, where one just guesses one's ability after a task or before. There's also self-reported behaviors. This often comes in the form of the metacognitive awareness inventory and is quite common in education, where students rate which actual behaviors they engage in while learning and studying. In order to get at something a little more behavioral, some people opt into looking through students' discussion forum writing or something of the sort to see how metacognitive their language use is, and other behavioral measures in these sort of open-ended online environments. And I'm really interested in self-assessment. It's relatively easy to capture. It simply requires assigning something and asking people to rate their ability. And most of the research so far in self-assessment involves questioning people's accuracy specifically, which makes sense because it's important to have a sense of what we do and don't know in order to study the right things and especially to learn independently. But a lot of the research has discovered overconfidence in great swaths, especially with young children, though there are exceptions like in different domains. So weather forecasting seems to have more metacognitive ability in addition to sometimes just the format of things. So asking someone to rate their ability much later rather than immediately after a task might have some impact. And self-assessment is measured frequently via one-off judgments of performance. So just before or after a task, asking for a score or ranking estimate. And then also via confidence judgments. And these are typically made throughout a task, but can just be placed in multiple locations throughout a task. I've done some work with one-off judgments, but there are some benefits to looking at confidence. So these involve sequential judgments, and therefore you get multiple judgments per individual in your study, allowing for you to actually explore individual variability in metacognitive ability. And it's doing something quite different from just a one-off judgment. We're actually tracking how someone is tracking their ability throughout a task instead of just one final judgment. And here, in order to really access how someone is tracking their ability and not just completely refer to accuracy, we're taking a modeling approach in this paper. And I've done so before for one-off judgments, but hopefully the idea is that this might yield some different results. So in this talk, I'm just going to go over the framework of our model and then talk about how we've measured confidence and report some human data. So our model takes a Bayesian form. This seems like a rational choice given that this task of making sequential confidence judgments is in fact about updating beliefs given evidence sequentially. And then we're really interested not just in accuracy or inaccuracy or overconfidence, but in what reasons might account for someone's self-assessment judgment patterns. So this might be prior beliefs. So say you're taking a grammar test, your initial beliefs before beginning this task will depend heavily on whether you're a native English speaker or if you've recently taken a course about the heavy in writing or something. And then sensitivity to correctness is also quite relevant. So after each problem, how knowledgeable are you about about your accuracy on a specific problem? And then we're also interested in responsiveness over time. So to what extent is someone weighing the most recent evidence and adjusting their confidence beliefs accordingly? And this is what's really interesting about confidence, or these sequential judgments rather than the one-off judgments. Because of course we can actually study this with individuals making multiple judgments. So some specifications of the model. We're going to refer to the confidence of person P at time point T as theta, and the accuracy of this person at a given time as X. So this will be equal to 1 or 0 if it's a correct or incorrect response. And the difficulty of each item we'll refer to as beta. Since we're taking a Bayesian approach, this requires having prior and likelihood terms. So our priors are going to include someone's beliefs at the very first time point, so the confidence judgment they make before starting the task at all, so theta 1, and then the difficulty of each item. Our likelihood is the probability of getting the answer correct, which is where our data comes in, right? So we thought about how to exactly specify the likelihood and opted for this equation that's actually a one-parameter IRT model, or a RASH model. It's commonly used in the educational stats literature, and it allows us to kind of think of our participants as intuitive statisticians as they're going through their problems. But this particular approach assumes that participants do have perfect knowledge. So we need to account for that by adding in some error to the likelihood term. So in order to account for people having imperfect knowledge, we add a term epsilon, which is essentially our error. It's the probability of being incorrect in your judgment after a particular problem. And that's just going to tweak the likelihood depending on how much error an individual has. And then our posterior, where we're trying to capture each person's ability belief at each particular time point. So after the first time point, which is our prior belief, in this graphical representation, we can see all of the layers and how all the things interact. And there are 3 specific parameters here that we're manipulating in order to see which reasons are more salient for different people. So the first parameter of interest is our mean over the prior on ability. So mu theta is if theta 1, our first ability belief, is normally distributed with mean mu theta. That's how we're going to manipulate the prior beliefs about ability. Then we have our epsilon parameter right here, which again is our error term, manipulating the likelihood and therefore the sensitivity to correctness after each individual item. And then thirdly, we have this parameter that we'll call sigma dynamic. And that is influencing each confidence judgment. And it represents someone's responsiveness to the most recent evidence. And to just see in action how manipulating these different parameters plays out, this is how we're depicting our data. So each bar here represents one problem and they're labeled on the x-axis. And then we have our confidence rating up on the y-axis. Each grayed out bar represents an incorrect response and the white bars are correct responses. So this random set of corrects and incorrects we generated to come up with a set of model simulations. So in a baseline version for this person, where we set all of the parameters equal to 0. So the mean over ability is pretty average, there's no error and no dynamics. We end up with a graph that looks like this, where you can see that after an incorrect response, someone's confidence decreases. After a correct response, it increases. And in particular, after a few correct responses, their confidence keeps climbing. And then after multiple incorrects in a row, it starts to descend more and more at a fairly steady rate. So this is our baseline. And then if we want to manipulate our prior via this mu theta parameter, if we increase it, we see that everything essentially just shifts up. And if we decrease it, the confidence estimates all pretty much just decrease on average. And now if we change the likelihood, we end up via the epsilon parameter and increase it by small amounts, we can see that there isn't necessarily as much of an increase in confidence after a correct response or decrease after an incorrect response. So just a little less sensitivity there. And then our dynamic parameter, which adjusts our dynamics, if we make it quite large, say 2, we can see these huge shifts happen. So there's kind of an increasing rate of confidence happening compared to when that dynamic parameter was 0. So just to reiterate, these are the 3 parameters that we're manipulating, and they have very different effects on confidence over a task, and it depends heavily on the sequence of corrects and incorrects, as we'll see with some participant data. And then because we are talking about this responsiveness idea, and it's a new thing in the models that I've been making, we're interested in whether this is even relevant. So we built 2 sets of models. One is a static model where our dynamic parameter is 0, and our dynamic model where we're saying it's non-zero. We're going to compare these 2 directly to see whether it's worth even manipulating the dynamic parameter and if there's individual variability. So we collected human data to fit our models too. We had 179 participants on MTurk solve 20 multiple choice algebra problems, and the task looked like this. First, they rated their confidence on a scale from 0 to 100, solved a multiple choice math problem, algebra problem, and then more confidence, and so on. For our model simulations, we had to run a set of simulations for each individual. So we ran thousands of simulations for each participant, where we looked at all possible combinations of the 3 parameters that we decided on. So for the static and dynamic model, we looked at values between -3 and 3 for mu theta, values up to 0.5 for epsilon, and for the dynamic sigma, we went all the way up to 6 for our dynamic model. There was relatively good distribution of scores achieved on this task. Meaning, yeah, we didn't just have any sort of floor ceiling effect. And this is an example here of one participant and what it looks like to fit the models to their data. So the blue triangles represent one participant's data, so their confidence, their estimated confidence. And then they have a score of 14, but you can see that the incorrect responses are fairly well spaced out. And in cyan, the circles, we can see the static predictions. And for the static model, the best fit static model, in looking at all of the possible static models, we took the one with the smallest sum of square errors when comparing to this participant's data. This particular model had a mu theta of 1, so higher ability prior beliefs, an average sort of error, and the dynamic model had quite similar terms, but then a higher dynamic parameter. And then because these models are nested, we're able to see if the dynamic model is fitting the data significantly more than the static model, and in this case, it was significant. Here's another participant for whom there was a significant difference and the dynamic model fit the data better. For this person, they had a much lower prior, but really were quite sensitive to their uncorrectness and quite responsive. And then here are a couple of other examples. In these cases, the models fit the data equally well, but we can just see it's cool to look at how drastically different people's data can look. And I obviously have so many more examples of this, but it was important for us to compare all of the data at once to see if the dynamic model was a better fit. So looking at an aggregate of all the participants, the dynamic model was in fact a better fit to the data. And then if we look at the parameter distributions, we see that there is a pretty good spray of different mu theta values, of different epsilon values, and different dynamic values. So in conclusion, the dynamic model is indeed a better fit overall, but there is a ton of variability. So it's not necessarily worth assuming that people are going to have a non-zero dynamic parameter. And one thing that stuck out at this stage was there was a kind of a spike of low ability priors, meaning people are less confident in their prior beliefs in algebra specifically. So it'll be interesting to compare across new domains. So future work is just going to compare this more to our aggregate data, look at more domains and contexts, and I've already collected other data and also in actual educational domains. So I just want to thank my advisors again. Couldn't have done this without them. Thank you all for listening.